Okay. Let's finish related rates. And just a few more examples just to get the idea home. To make sure we all remember the steps. I'm not going to give you the steps, you kind of just have to know how to do them. So the idea behind this topic was, of course, if quantities are related and we know the relationship between them, then their rates are also related, and we can get to that relationship by just differentiating the original relationship. And so, but there's a very strategic way that we approach this to make sure that we have all the information that we need moving through the problem. So we're just going to continue that guide to make sure that we all remember those steps. Not problem 2, problem 4. I think we did the first 3 already. So this one says the volume of a sphere is increasing at a rate of 5 cubic feet per second. How fast is the radius increasing when the radius is 2 feet in length? And it gave you a formula. So, what's our first step? Read. Right? Make sure you're aware of all the information. First of all, you need to recognize that it's a related rates problem, and that comes in when you realize that they're telling you about the rate of change of a quantity, and they ask you for another rate of change of some related quantity. So the first thing is to actually read it. What's the second thing? Draw a diagram. Right, so make a pictorial representation of the situation so that you can come up with ideas for a formula. That's the main reason why you would do it. In this case, we can skip it, right? Why? Because they gave us the formula. Right, the relationship is given, it's not really something we have to figure out. The formula for 4 is given. Right, remember the whole point of drawing a diagram is to figure out a relationship, right? So when you drew that diagram, for example, of the ladder leaning against the wall, where you're like, oh, that's like a right triangle. Oh, I know a formula for that. Pythagoras is there, right? The whole point of the picture is to get you to come up with the formula. But if the formula is given, you actually don't, you can skip this step, but you still consider it and you just move on in order. So the third step would be to do what? Yeah? Right, write down what you know, the information you know, the rates you know, and the rates that you want to find. So here, what are we told? The volume is increasing at 5 cubic feet per second. And we know that V is the symbol for volume because that's what it says here. So what does that tell us? The volume is increasing at 5 cubic feet per second. How can we write that down? Yep.
Derivative of the volume over the derivative
dV dt equals 5. Right? It's positive 5 because it's increasing. And that's it. Then right after that they asked us the question, how fast is its radius increasing when the radius is 2 feet in length? So here we want dr dt when r equals 2. What was step 4?
Right equation.
Yeah, come with a relationship. Write down the equation that relates all the variables. And here, in this case, it was given. Right? We know that the volume. What was the volume of the sphere? Now, usually, step 2 is what helps you come up with this, but this was actually given. So we could skip step 2 and jump straight to that. Once we have that equation, what do we do now? you need to find the derivative, because now we need to start plugging in rates to figure out other rates. Rates aren't present here, so you get them by actually taking derivatives. That's where the rates come in. So we use implicit differentiation with the chain rule to differentiate with respect to t. So derivative of v is dv dt. And what's the derivative of the right side?
It's forward 3 pi.
Yeah, 3r squared is the derivative of this. The 3 comes down, you can cancel that. So it's the 4 pi r squared drdt. Remember, it's the chain rule because r is a function of t, so when you differentiate it, you have to multiply by its derivative. And step 6. Plug it. So you plug in your knowns, solve for your unknowns, and as we saw last time, the only one hiccup that could potentially happen here is that you won't have all the information to plug in at this point. But in that case, you just go back to step 4, solve for whatever information you need, and come back here and plug it in. But in this case, I think we actually have everything. So we know dv dt is 5. This 4 pi is just a constant. We want r squared, but our r is 2. And our dr dt is what we want to find, so we don't know that. And so now we solve for what we want, which is dr dt. So this means that 5 is equal to 16 pi dr dt, which means that dr dt. And this is in feet per second. Although, as I said, I don't particularly care about the units, I'm just letting you know. So those are the steps. Always these 6 steps, always in this order. There are times when you can skip over certain steps when you don't actually need them, and you just realize that you need this step to know what to plug in here. You need the diagram step to figure out this. And you need this to figure out that. So you kind of need to go in this order, but sometimes you can jump over certain things. Any questions? Let's move on to the next one. 5. 5 has 2 parts. What's the related rates? It's the same 6 steps. Let's just go with so this is part A. So it says the side length of a cube is increasing at a rate of 2 inches per minute. When the side length is 3 inches, A, how fast is the surface area increasing? So we read the problem's related rates, we see all what the situation is. Our diagram here is a cube. And so now we just want to draw and label the diagram. How do you want to label this diagram? How do you want to label the cube?
Which side is S?
You want to call it S? Sometimes I don't like using S because it can be confused with 5. Let's use X. Okay. So that side length is X. What's the width?
X.
It's also X. And the height? It's also X, right? Why? Because it's a cube. So we're given that information. There are other descriptions that I could have told you. They could have said something like the length is twice the width, in which case one of these would be 2x and so on. So it's important to read. But here it's a cube. We know all the side lengths are equal. And so we can just label them all with the same variable. So what do we know? We know dx dt. It's increasing at a rate of 2, therefore it is positive 2. And what do we want? Is if I let A be, let's call A the surface area. So what we want is the rate of change. How fast is the surface area changing when x equals 3? So what's our equation here? We need an equation that relates x and a. These are our two variables.
A equals 6x squared.
A equals 6x squared. Surface area is the area of all the faces. You'll notice that on a cube, each face, if you isolate it, it's just a square. It has length and width x. So the area of each face is length times width, which is x squared, and there are 6 faces. So it's 6x squared is the surface area. Right, so on this diagram, you can sort of use this to help you like count off the faces. You can realize, oh, there's the top, there's the bottom, there's the 4 sides, and that makes 6. And again, it could be possible for someone to say something like, oh, it has no top, it's an open cube that you can put something into, in which case it would be 5x squared. So it's important to actually read so that you really understand the situation. But yeah, that's the equation. Once you have the equation, now we just differentiate the equation. Derivative of A is dA dt. Derivative of that is 12x dx dt. And so now, it says we want the rate of change of area when x equals 3. So we're going to plug these in. dA dt we don't know. 12x we know is 3. dx dt we know is 2. So what is that? 72. And in this case it's in inches per minute. So this is inches squared per minute. This area is in inch squared. It's in square units. Let's do another example. We'll do another example, just to really emphasize that what you really need here is this template in your head when you're going to related rates. So once you read a problem and you realize it's a related rates problem, you automatically know, okay, there's this template that I have to fill out, 1, 2, 3, 4, 5, 6. And by the time you get to the 6th step, you're done. Just move on. Our diagram is going to be the same. It's the same structure. The difference is they're asking about something different here. They're asking about the volume. How fast is the volume changing? So you can see, you can take the same problem and you can tweak it all sorts of ways. Like I can put the same problem on the next test and just tell you, okay, it's the cube is open. How's the surface area changing? Or for whatever, it's a box and the side length is twice the width or something like that. And how is the volume changing in that case? I can say all sorts of things. I can tweak any of these problems in any way, so it's very important to sort of read. So read the problem, diagram is the same. Now we care about volume, so I'm calling volume big V. What we know is the rate of change is 2, that's the same. It applies to both parts A and B. What we want is different. In this case, we want dV dt. And that's going to change our equation, which is going to change this equation, which is going to change what happens here. So what's the equation that relates B and X? How do you find the volume of a cube?
X cubed.
X cubed. Length times width times height. Differentiate that. Derivative of V is dV dt. Derivative of x cubed is 3x squared x dt. So now we're going to plug in dV dt. We don't know, it's what we want to find. We have 3. Our x is also 3. And our dx dt is 2. And this is volume, so it's going to be in cubic inches per minute. So what's that? 54. And yes, it's like beating a dead horse, but we're going to do it again. Related rates, exactly the same template applies. And we're doing problem 6, the last one we're going to do. The others you can try on your own for extra practice. If you want to do some things on top of the homework, or if you're reviewing for like the third test, then you did all the review problems, and you did all the homework problems, and you want some extra problems to practice, you can practice on these. But they're, I'm not going to go through those. Odds are the first 6, it's a problem type like that I put on the test. I wouldn't put the other ones. So yeah. The radius of a circle is increasing at a rate of 1 meter per minute. What is the instantaneous rate of change of the area of the circle at the instant the area is 4? That should be square meters. It says cubic meters there, but it should be square meters. So 1, related rates problem, we read it carefully, see the situation that's going on. 2, you realize that what's happening here is that we have a circle. I'm going to call the radius r. It also asks us about, it mentions the area, so I'm going to call A to be the area of the circle. So I do my diagram, I define the variables, and what do I know? It's increasing at a rate of 1 meter per minute. The radius is, so that's dr dt is 1, positive 1, because it's increasing. And what we want is dA dt when the area is 4 pi. Meters squared. So the equation here,
A equals pi squared.
so this picture should bring up fond memories from high school geometry class. You know, it's not gonna. So when we differentiate that, derivative of A dA dt. And derivative of pi r squared, so that becomes 2 pi r dt. just plug in what we know what we want to find, right? So dA dt we don't know is what we want to find. dr dt we know is 1, but do we know r? What's r? It's not in any of our given information. It's not something that we know ahead of time. So what do we do? Yeah?
Put 4 pi back into the A equals pi r squared equation.
Go back to step 4. So we got to this part. Notice that here we need r. Right? So what we do is you go to step 4 to find r. Now in step 4 we know that a is equal to 4 pi r squared. Remembering the last one. And so this would mean that if my a is 4 pi, you plug that in. Then that would mean you divide both sides by pi, you take the square root of both sides, my r would be 2. To the square you get plus or minus 2, but it's a radius so it has to have a positive length, so it's just 2. So I wasn't given that information, but I can figure it out from step 4. So now I can finally plug things in. My dA dt, I don't know, it's what I want to find, so I leave that. Equals 2 pi times r, which we just found, times dr dt, which is 1. So that gives us, it's also 4 pi meters squared. And that's related rates. I mean, after you do like 6 problems, it's not terribly exciting anymore. It's just like, it's kind of. But hopefully it'll be easy, something that you can get a lot of points on for the next test. It's an important topic, but in calculus it's very streamlined. You kind of can pick up on a lot of information. And as I said, I'm most going to ask you about geometrical shapes. So you should kind of just review some formulas for that. So yeah, that shouldn't be bad. One thing though that I didn't expect to be too bad, but when I started grading it, it seemed like a lot of students have trouble with it. I put a similar question on the test for my other calc classes. I haven't finished grading, but I grade by questions, so I grade all the question 1s and then all the questions 2. So I'm going through question 1 and it seems like a lot of people have trouble with it. So honestly, when I wrote it down, I didn't think it would have a lot of trouble, but if you want to find the derivative by the limit definition here. What's the formula?
X plus 8.
What is that? Oh, limit of 8 as
Limit.
h plus 0.
As h approaches 0. Right, now everyone's talking like, yeah, I remember that from yesterday. Okay. And so when you started to plug this in, what happened here?
3 times x plus h minus 2 over x plus h minus 3x
Parentheses.
plus
Okay, so, and again, remember the goal is to cancel the h. We have a complex fraction here. The quickest way to simplify it is really to just multiply top and bottom by the LCD. But I kind of do something else before. Let's simplify a little bit. This I can write as 3x plus 3h. And so I can get the 3x out of the way. So I have this there's no harm in rearranging here. So let's just do that. So I have that. And how did you guys, did most of you guys get to that point?
Yeah.
Okay. And after that everything went up. what would you do here?
Top and bottom of X.
Yeah, that's like the straightforward way. I would have done it a slightly different way. I would have separated them first because I don't want to have to deal with this guy. I mean, technically he's not really complicating things. The complicating things are these fractions here. So one way how I would have done it is probably just to separate the two. So I have the 3h over h, and then I have this guy. And so this guy, there's just a 3 hanging out by its own. So I just kind of ignore it and then I focus on this. But honestly, you could have done multiply top and bottom by the LCD at this point, and eventually you would get to the same answer. It's not going to change anything. Right? And so now I'm just focusing on simplifying this part, which it's a complex fraction, so multiplying and dividing by the LCD is what I would do. So there's this 3 just hanging out. And here I'm going to multiply by x times x plus h over x times x plus h. So then I take this, multiply that, the x's cancel, and so I just get 2 times x plus h minus, multiply this by that, the x plus h is cancel, so that's just 2x over h times x plus h. This we can distribute, this will give us 2x plus 2h, and so the 2x's will cancel. So that just becomes 2h over that. And now the h is cancelled. I mean, I could plug in there, but let's just write another step to clean it up a little bit. So it turns out that that's what we have. And at this point, you can plug in h equals 0. The denominator won't be 0 there. And so I just get 3 plus 2 over x squared. Which, by the way, we know the power rule now, so we could actually check it. So what you could is you could go in the corner and you could check. And you know that if this is the case, 3x minus 2 over x, you could rewrite that as this. And then do the power rule. Derivative of 3x is 3. This guy, you bring down to minus 1, subtract 1 from the power, negative times negative makes it positive, so it's 3 plus 2x to the minus 2, and which gives you this. But yeah, don't forget your algebra rules. At this point, it's a complex fraction. You see fractions inside of a bigger fraction. Just multiply top and bottom by the LCD. That's the quickest way to actually get rid of it. You could have separated the 3 from the beginning, but it's not going to be terribly much more work if you didn't, honestly. So I mean, you'll see this when I post the solutions, but let me do the other version. Let's say you didn't realize or you didn't want to separate the 3. When I write the solutions, I probably write down this version. But let's say you got here, and you never thought of separating the fraction into 2 parts. It wouldn't have mattered much. You still just multiply by x times x plus h. You're going to have to deal with something over here that you wouldn't have to deal with otherwise, but it's not bad. So now, what would happen is I'm going to take this times the 3. So I'm going to have 3h times x plus h. This times that, I would have 2 times x plus h. And this times that, I would have minus 2x all over h times x plus h. And so now I just distribute and group things together. This is plus 2x plus 2h minus 2x, and these guys would die. And h is a common term at this point that I could factor out. I have 3x times x plus h, y plus 2, all over h is cancelled. And I can plug in h equals 0, and I would get 3x squared plus 2 all over x squared. Which again, at this point you can split the fractions up if you wanted, and get 3x squared over x squared plus 2 over x squared. You get the same thing eventually. So, I mean, this step would look a little different, but it's not that much different. But yeah. Anyway, I'll finish grading those and give it back to you, if not Friday, by Tuesday. And we'll continue tomorrow with continue on Friday with maximum and min values. The homework for this is actually due, so do your related rates homework for
The problem is that